This lesson will be about analyzing graphs of functions. This is section 1.5 in your textbook. The essential question for this lesson is, what tools are available to analyze the graphs of functions? We graph a function much like we would any equation in x and y. And as you can see from this example here, we have a function that's graphed. We have the x-axis, which is the horizontal axis, and we've got the y-axis, which is the vertical axis. Now our function itself is represented by this line, and we're going to say this line is y equals f of x. Okay? So that is our function. Now, we might ask ourselves, what is the domain and what is the range of this function? So let's start with the domain. And the domain is basically the x values. What are the possible values of x for this function? Well, if you look at the x values, we can see that it goes from -5 to +4. However, notice on the line at -5, we've got an open circle. Well, what does that mean? That basically means that x cannot equal -5. It can get really close to -5, but it can't equal -5. So we might think of the domain as being written as follows. We could say that -5 is less than x, which is less than or equal to 4. Because it can equal 4, but it can't equal -5. So this would represent the domain. Now, what about the range? Well, the range is the y values. Now, if we look at the y values, we start at -2 and we go all the way up to 3. But again, notice at -2, we've got the open circle. So the range, in this case, would be -2 is less than y, is less than or equal to 3. So the range of this function would be -2 is less than y is less than or equal to 3. Now let's talk about the vertical line test for functions. This is a way that you can look at a graph and determine whether the graph is the graph of a function, okay? Or is it just a graph of a relation, okay? Earlier lessons we talked about the difference between relations and functions. Well, this is a way we can look at a graph and determine, is this a relation or is this a function? All right, now here I have two graphs of equations. The one on the left is y is equal to the absolute value of x -2, and the one on the right is x is equal to the absolute value of y plus 1. Now, the vertical line test says that if I draw a vertical line and the vertical line only passes through the graph in one location, then we have a function. If, however, the vertical line passes through the graph in 2 or more locations, we do not have a function. So now, notice the two red vertical lines. The one on the left obviously only passes through the graph in one location, and we can see that right here, okay? But the one on the right passes through the graph in 2 locations. So we've got a place right here, and we also have another place right here. So it's obvious, therefore, that the one on the right is not a function, because for a given value of x, somewhere between 3 and 4, there are 2 values for y. On the left, for a given value of x, there is only 1 value of y. So the one on the left is a function, and the one on the right is not. Now we're going to talk about the zeros of a function. The zeros of a function are simply the x values for which the function is equal to 0. Or thought of in another way, they're the x-intercepts of the function. So now we have an example that I'd like to go over. We have a function, f of x is equal to x squared minus 4x, and we have its graph. So I want to find the zeros of the function. So that means I'm going to set f of x equal to 0 and solve for x. So if I set x squared minus 4x equal to 0, I factor that out and set each of the factors equal to 0, I end up with x equals 0 and x equals 4. And as you can see from the graph, those are indeed the x-intercepts, or in this case, the zeros of the function. Now let us talk about increasing, decreasing, and constant functions. Using the previous example, we can see that from x equals 2 on out to more positive values of x, so from 2, any value of x greater than 2, the function is increasing. In other words, the f of x value or y value is going up. So to the right of x equals 2, the function is increasing. To the left of x equals 2, the function is decreasing. So for values of x less than 2, the function is decreasing. For values of x greater than 2, the function is increasing. Now this particular example doesn't have any constant region. So a constant region would be where the y value remains the same for an interval over the x value. This particular function does not have a constant area. Now what do we mean by relative minimum and relative maximum? This is where the function changes from being decreasing to increasing, or from increasing to decreasing. It's a transition point, if you will. And you'll notice that at the point, using our previous example again, of x equals 2, y equals minus 4, the function is going from a decreasing to an increasing mode, so therefore that is a relative minimum. Okay? If it were going in the other direction, from an increasing to a decreasing, it would be a relative maximum. Now previously we talked about symmetry of a graph, okay? Now, symmetry, we talked about symmetry with respect to the x-axis, symmetry with respect to the y-axis, and symmetry with respect to the origin. Well, it just so happens that if a graph is symmetric with respect to the y-axis, it is said to be even. And if a graph is symmetric with respect to the origin, it is considered to be odd. Another way of looking at it is an even function, or a function is even, if whenever you plug in minus x for x in the function, nothing happens to the value. For example, if you had a function f of x is equal to x squared, and you plug in minus x for x, you get minus x in parentheses squared, which is simply equal to minus x times minus x, or plus x. And as you can see, you still have the original function. So this function is considered to be an even function. Now similarly, a function is considered to be odd whenever f of minus x is equal to minus f of x. In other words, you plug in minus x for x in the function, and you get the negative of what the original function was. So if we take another example where we have a function g of x, and that is equal to x to the third minus x. And now if I plug in minus x for x in this function, I'll have minus x in parentheses cubed minus a minus x in parentheses, which yields minus x to the third plus x, which is simply the negative of the original function. So therefore, this function is odd. So this can also be seen by looking at the two graphs that I've shown here. The one on the left, the red graph, is symmetric about the y-axis, so therefore that is obviously even, while the blue graph, which is symmetric about the origin, is obviously odd. Now I would like you to find the zeros of the function f of x is equal to x squared minus x minus 6 and determine whether the function is odd, even, or neither. Post your answers in the drop box.